So today in this video we're going to talk about the hybridization. So what is actually hybridization? Why we need to understand the hybridization, or why do we need to know the hybridization? So previously, like we have learned VBT. So according to VBT, we have seen that two different subshells combined and they form a bond. Like we have seen P combined with S that form a sigma bond. So that was VBT, valence bond theory. So VBT was not able to explain about the equivalence of bond. Equivalence of bond like bond energy, bond length and bond strength. It was unable to explain all these concepts. And to explain about the equivalence of bond, parameter concept of hybridization is introduced. So if you want to understand the bond parameter, we need to know the hybridization. So let's check a compound which is like CH4, which we call the methane. In methane, if we go according to the valence bond theory, let's go according to valence bond theory. We know carbon it has atomic number 6. So if we want to write its electronic configuration, it is 1s2, 2s2 and it is 2p2. Now if we try to draw its orbital diagram, so here it has 2 electrons, one is plus half and minus half. 2s2 again has 2 electrons plus half and minus half. And if we want to go through that p, and it has like 2 unpaired electron. Now this is its ground state. So in its ground state, the methane is like this. So when it want to make a bond, it will go into excited state because it is needed it needed the 4 unpaired electron to form the 4 bonds according to VBT, valence bond theory. So these the valence electron, these are called the valence electron because they are in the valence shell. Valence shell here is the second shell. So we're going to excite only the valence electron. So 1s2 will remain same and that valence electron will go excite to get unpaired. So what's going to happen? This electron pair will go into that empty one here, and that's how we have seen the bomb was forming in case of like methane. Now that is known as the very first excited state of carbon atom. Now we have actually 4 different hydrogen atoms. So here one hydrogen atom orbital is there. Here the rest of the, here also we have 4 hydrogen. So here also 1s, here also 1 hydrogen and here also 1 hydrogen. So we have these 4 hydrogen and they have like unpaired electron. So these are, we have 4 hydrogen. Okay. So this hydrogen will form a bond. These together will form a bond. This will form a bond. This will form a bond and this will form a bond. So actually it is s orbital. It is like p x, let's say it is py and it is pz. So now if we try to form the bond, we have, let's try to draw its structure. Like here we have now 3 axes. This is one axis, this is another axis and this is another axis. Let's name it as x axis, y axis and z axis. Now we want to draw the structure of CH4. What we gonna see? It has 1s electron, it has 1 px, it has 1 py and it has 1 pz. So let's say it's pz orbital. Now we have all the identical hydrogen s orbital. So this one s gonna combine over here, one is gonna combine over here, and one s gonna combine over here, and one s is forming bonding with one s. So actually we have 4 types of bond. One is like this is SS bonding, this is SPZ overlapping, PZ overlapping, this is SPX overlapping, and this is SPY overlapping. So these type of overlapping we have. Now if you want to see the structure, what the structure we see here, like one is SS bond and 3 here SP bond. So one is SS bond and one is SP bond. So like we talk about like bond strength, bond angle, bond length, all are we are getting different. These are different according to the VBT. So that is different according to valence bond theory. Now if we look at the original structure of methane CH4, it has, but actually all 4 bonds in methane are similar, are equal. Bonds are equal means, and bond angle we found is, bond angle we found is 109 degree 28 minutes. So that is the bond angle we find. So bond length, bond energy, okay, if we talk about the bond energy also is same of the all these. So these bond parameters are same, but according to VBT we are observing that we have 3 different types of compound. According to VBT we will be observing like we have 3 bonds which are at 90 degree and 1 that is non-directional bond. So means when there is SS overlapping, we have seen when S overlaps with S, there is no direction. But this type of, when PX overlapping with S, this is this particular direction. So these 3 are at the 90 degree bond angle and 1 is non-directional. So here we are getting 2 different type of bond. Even these bond have 90 degree bond angle, which is not the actual compound of the methane. Actual compound of the methane is 109 degree 28 minutes and all the bond lengths are equal, and these all bonds are sp3s. So in methane we get all bonds are actually sp3s with bond angle 109 degree 28 minutes. So process of intermixing of pure sp and d orbitals to produce a new set of orbitals, that is known as hybrid orbital, and it is known as hybridization. So that process of intermixing to produce a new orbitals, this is known as the hybridization. So hybridization is first of all a hypothetical concept. This explains almost the properties of the compound. That's why we use it, and it is a hypothetical concept. And number of hybrid orbitals produced are equals to pure atomic orbital involved in the intermixing. So if we have like mixed 3 orbitals, so we will be getting 3 multiplied by the hybrid orbitals. So if we have 3 orbitals going to mix, so we will get 3 hybrid orbitals. So hybrid orbitals are identical in size, shape, energy. So all have same size, shape and energy. All the hybrid orbitals are similar. And if we want to represent the hybrid orbital, it is represented by like this. So it is a small lobe and it is like a large lobe. So that's how we represent the hybrid orbitals. So only those orbitals that involves in intermixing which have same or nearly same energy. So like we cannot intermix like 1s with 2s because they have a lot of energy different. We can mix the 2s and 2ps. We can mix that. We can mix like 3p and 3d. Okay. So they always must have the same or nearly same energy. Energy difference should not be high. So what are the method to determine the hybridization? So is equal to the steric number is equals to the number of sigma bonds, the number of lone pairs of electron on the central atom. So it is the summation of both the quantity, how many number of sigma bond and number of lone pair on the electron on the central atom we have. So what the steric number gives? It gives the total number of hybrid orbitals. How many total number of hybrid orbitals we are getting, that we calculate by steric number. So now let's see some steric numbers and what is the hybridization and what are some examples of those compounds. So let's see, like we have, if steric number is 2, the hybridization we take is sp. An example is like BeCl2. If steric numbers come out to be 3, we take it at like sp2 and it is given by the BeCl3. If steric numbers comes out to be 4, we could write it as a sp3 and it comes out to be CCl4. If steric numbers is 5 here, it is sp3d and it comes like example is BCl5. If steric number we have 6, it is sp3d2 and it is SF6. And if steric number is 7, it is sp3d3 and the example is IF7. So let's do some exercise like determine the hybridization of the central atom in the following. So if first of all, whenever it is asking the hybridization, if it is not mentioning the central atom, indirectly we have to assume that we have to calculate the hybridization of the central atom itself. So I'll first appreciate that you pause this video and write down these illustrations and try to answer by your own what could be the possible hybridization of these compound. So let's see here if we have I3 plus. So if we see here how many I having 2 bonds I and I. Okay, so here, so if we see on the central atom, we will be getting that it is sp3. It has 1, 2, 3, 4, 2 sigma bond and 2 lone pair over here. So steric number here it is it is having positive charge over here. So steric number is 4. If we talk about PCl5, it is also sp3. Here steric number is 4. H2 amino oxygen has 2 lone pair and 2 sigma. This is the structure of H2O. So here we have 2 lone pair and 2 hydrogen. So steric number here is 4 and that's why it is sp3. Ammonia also steric number is 4. It is sp3. PCl5 steric number is 6. No, here it is 5. That's why it is sp3d. If we talk about XZF4, it comes out to be sp3d2. If we see 4 bonds pair, and we will be getting like 2 XZ. It has 4 bonds and remaining we have 4 electrons. So 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6. If we talk about 6, 3, 4, 5, 6. That's why we are getting sp3d2. ICl2, if we see, we will be getting like sp3 or D. So if we look like here, iodine is surrounded by 2 chlorine atoms and here iodine having a negative 1 charge and here we are getting 3 lone pairs. So it is hypervalent compound. Okay, so it is sp3d. If we talk about xenon OF4, okay, XeOF4, so here we will be getting the hybridization is sp3d2. So 4 of fluorine and 1 oxygen. So we have to count the sigma bond only here and the lone pair. So that's how we will be getting here. And 1, 2, 3, 4, 5, 6. In case of 6, we write it as sp3d2. Now in case of X sulfur OXF4, SOX4, that come out to be sp3d.